Hello everyone, my name is Pritam Kumar and I'm currently pursuing my BTech first year at Carnegie Institute of Technology and Sciences. Today I'm going to explain my computer organization and architectures practicum number 7, which is titled as Cache Mapping Technique Analysis. In this video, we are going to explore cache mapping techniques and understand how cache improves computer performance using MATLAB simulations. So basically, we'll cover three types of mapping techniques. First one is direct mapping. Second one is associative mapping, and third is the set associative mapping. And the real world impacts like gaming, multitasking, and streaming, so on. So let's get started. So, what is cache? Cache memory is small, high-speed memory located close to the CPU. It stores frequently accessed data, so the CPU doesn't have to go all the way to the RAM every time. Think of it like keeping your most used apps on your home screen instead of searching it every time. So the first program is about explaining how cache improves the computer speed in real-world applications like gaming. So first, I clear the MATLAB environment. CLC clears the command window, and clear removes all the variables. Close all closes any open figures, and this ensures a clean start from the program. So basically, here I define a cache size as 4, which means the cache can store 4 blocks at a time. Here I initialize the cache with -1 values. This represents that all the cache positions are initially empty. So this array represents the sequence of memory blocks accessed by the CPU. Repeated values simulate the real world scenarios like gaming or streaming. And I initialize the counters for cache hits and cache misses here. This line prints the table header for better output formatting. And this loop runs through each memory block one by one. And I extract the current block from the sequence using the line block equals to memory blocks. And in the if statement, I check if the block already exists in the cache using isMember. Result is equals to hit that line. If the block is found, it is a cache hit, and I increment the hit counter by 1. If it is not, that is the else statement, then it is a cache miss. So I mark it as a miss and increment the miss counter by 1. Here I apply the FIFO replacement. First in, first out, the oldest element is removed and the new block is added at the end. And this prints the current block whether if it is a hit or a miss and displays the updated cache state. And end this ends the loop after processing all memory blocks. And finally, I display the total number of hits and misses. If I run this program, the output will be shown in this way, the table as well as the total miss and total hits. Total hits are 2 and total misses is 10. The second program predicts what happens if the cache memory is too small when running multiple programs. So for this program, the structure is similar to the previous one. The main difference is the cache size is smaller, so more replacements occur, leading to higher misses. Everything is almost the same here. If you run this, it will be shown in this way, and hits and misses are shown. And the third program, it justifies why industries use different mapping methods like direct associative and set associative. So basically, this program compares two techniques, direct and associative mapping. So the direct mapping part uses this line index equals to mod block comma cache size, which fixes the position of the data in cache. In associative mapping, we use isMember, which allows the data to be stored in anywhere in the cache. This flexibility reduces misses compared to direct mapping. This is the output. Direct mapping hits is 2 and misses are 6. In associative mapping, hits are 0 and misses is 8. So fourth one is how frequent cache misses could affect video streaming or online classes. This program simulates the real world scenarios like video streaming and online classes where data such as video frames or packets are accessed repeatedly. The structure of the code is similar to the previous programs, but here the focus is on cache miss rate and its impact on performance. So here we define a smaller cache size of 3, which makes the system more prone to the misses. The data stream array represents incoming video data or packets being accessed by the system. And using isMember, we check whether the data is already present in cache. If yes, it is a hit, meaning fast access. If not, it is a miss. And the data is loaded into the cache using FIFO replacement. And at the end, we calculate the miss rate using number of misses divided by the total data access. This is a formula with the line 45. This is the output. A higher miss rate means the system is frequently fetching data from main memory instead of cache. In real-world applications like streaming or online classes, this leads to buffering or lag interrupted playback. Program 5 determines which mapping method is more efficient for multitasking systems. Here the cache is divided into sets. It is about set associative. Here the cache is divided into sets. Instead of mapping to a single index, we first find the set using modulo and then search with that set. This reduces the collisions and improves performance compared to the direct mapping. So this is how the output looks like. Sets are divided and then it's done. Sixth program is about what happens if two memory blocks map to the same cache line in direct mapping. So basically in this program, multiple memory blocks map to this same cache index. So this causes frequent replacement, which increases cache misses. This problem is known as collision in direct mapping. Seventh program is about how programmers benefit when cache mapping reduces data access time. Here I introduce access times. If it is a hit, the time is 1 unit. If it is a miss, the time is 5 units. So this shows how cache improves execution speed by reducing access time. Eighth program is to evaluate why cache memory is more expensive than RAM, yet it is still necessary in systems. So cache versus RAM. This program compares cache access with RAM access. Cache is faster but smaller, while RAM is slower but larger. Even though cache is expensive, it reduces total access time significantly. Ninth program is about how poor cache performance could slow down banking or airline booking systems. Here are simulate systems like banking or booking. Misses introduce higher delay, which increases total system response time. This shows why efficient caching is critical in real-world applications. 10 program is about how cache mapping techniques can influence the design of modern processors. This program simulates L1, L2, and L3 cache. The system checks L1 first, then L2, then L3. The data is not found, it is fetched from RAM. This hierarchy improves performance in modern processors. So from this practicum, we can clearly understand that cache memory plays a crucial role in improving computer performance. Different cache mapping techniques have different characteristics. Like direct mapping is simple and fast, but suffers from collisions. Associative mapping is flexible but more complex, and set associative mapping provides a balance between the two. Through the MATLAB simulations, we observed how cache hits and misses affect system efficiency. Higher cache hits lead to faster data access, while frequent misses increase delay and reduce performance. We also saw real-world impacts in applications like gaming, streaming, multitasking, and also online systems where efficient caching ensures smooth and fast operations. So, in conclusion, cache memory is not just a storage component, but a smart mechanism that optimizes speed and performance in modern computing systems. Thank you.